actually make use of the knowledge of English, opposite, word and opposite. Then compound statements. Now, compound statements are statements that contains a number of simple sub-statements. For example, some students in SS2 study geography and some don't. From this statement, we have a universal set, which is a set or a collection of students who are in SS2. Then we have a set of students who are in SS2 who study geography, students who study geography. Then we have those that doesn't study geography. That is our A complement. That is the geography complement. We can represent this with a Venn diagram with our U as a universal set, our A as a set of students who study geography, and the A complement, which are the students who do not study geography. There is something for us to note. The complement of A and both mean, that is when we have approximate A and A apostrophe, we have both mean complement of set A. The Venn diagram are very useful for showing compound statement. Now we now go to conjunction, that is conjunction statements. Conjunction statements are statements whose sub-statements are linked by the relation and. For example, students who ate fried rice and drank Fanta. We can use Venn diagram below, that is the Venn diagram that we can see here, to represent this statement, where our universal set is students, R, those who ate fried rice, and F, set F, those who like Fanta. Now, the shaded portion blue gives the interaction of those that actually drank Fanta and also ate fried rice. We have set of people that ate rice, and then the set of people that drank Fanta. And in between them, that is where the two circles overlap, is the set of those that drank Fanta and at the same time ate fried rice. In set notation, the intersection of R and F, that is those that ate fried rice and drank Fanta, represent the conjunction of R and F. Symbolic logic uses the symbol intersection. Thus, R intersection F is a conjunction of R and F. A conjunction is true only if both of the sub-statements are true. Thus, the statement, the student ate fried rice and drank Fanta, is true only if the student satisfies both. That is, they satisfies both statements. That is, they ate fried rice and they drank Fanta. This is shown in the truth table below. We have the column of those that ate fried rice. We have the column of those that drank Fanta, and then the column of those that ate fried rice and also drank Fanta. This statement, let's now take it one after the other. Those that ate fried rice, true. Those on the same row we have true for those that ate fried rice and drank Fanta. Now the statement is true for R intersection F. But for the third row, where we have those that ate fried rice but does not drank Fanta, for R intersection F, that is those that ate fried rice and also drank Fanta, it is false. Because we can't have, the statement has to be true for both statements, sub-statements. Then when we have those that does not eat fried rice but drank Fanta, our R intersection F is false. That is no. It's not obtainable. That is, we can't, when you didn't eat fried rice, you didn't eat fried rice, but you drank Fanta, you can't say that you ate fried rice and drank Fanta. Now, when you didn't, we have a situation where a student did not eat fried rice, and also the student was unable to drink Fanta, then absolutely we can confidentially say that the student did not eat fried rice, and also he didn't drink Fanta. So it's false. Truth table for that means the table that we are having, that we just explained, is a table for there is a truth table for R union, R intersection F, which is our conjunction, where T is true and F is false. Now we now go to disjunction statement. Disjunction statements are statements whose substatements are linked by relation either or both. For example, students who either ate fried rice or who drank Fanta or both is an example of disjunction. In a set notation, the union R union F represents the disjunction of R and F. Symbolic logic uses the symbol union. Thus, R union F is the disjunction of R and F, which can be seen in the Venn diagram here, where we have the set of R overlapping that of F, and we have our universal set as a class. The student either ate fried rice or drank Fanta or both is true if either of its substatements is true or if they are both true. While it is only false if they are both false, as can be seen in the table below. We have a column for fried rice, we have a column for Fanta, and then we have our column for fried rice union Fanta. That is those that ate fried rice and also drank Fanta. I want us to recollect that the statement, for it to be true, it must be either true for one of the substatements, that is true if they are both true. It is true if either of the substatements, either, that is, all we just need is just for one of the statements to be true. Then our R union F will be true. Now, in a situation whereby a student ate fried rice and also drank Fanta, then our R union F is true. In a situation whereby a student ate fried rice but doesn't drink Fanta, that is, the Fanta doesn't get to its own side, or it has finished before he was able to get into his side, then R union F is true, because one of the statements is true. Then in a situation whereby the student was unable to get fried rice, but he was able to get Fanta, luckily he got Fanta, then our R union F is true. But in a situation whereby the students neither got fried rice nor Fanta, then our R union F is false. Thus, as we've seen in the table. Now, we now go to implication statement. In implication statement, there is always the substatement X, which is called the antecedent. That is the one that comes after, while the substatement Y called the consequence. That is the consequence of what you've done in our X, which can be represented as X implies Y. The arrow shows that Y follows from X. X implies Y is not the same as Y implies X. The statement X implies Y is sometimes called a conditional statement. For example, just as you can see, this Venn diagram, where set B is a subset of C in our universal set. Our universal set is a set of students in Bright College, and our set C is a set of students who takes part in a catering class. While set B is a set of students who can bake cake. Note that B is a subset of C. That is, B is a subset of C. That is, the symbol for subset is something like this. It's not a C, but it's an extended C. This means that if a student bakes cake, then the student also takes part in catering class. We can write this as statement T. If a student can bake cake, then the student takes part in the catering class. Statement T is really a combination of the following statements. That is, as statement X, a student at Bright College can bake cake. Who can bake cake? And as statement Y, a student at Bright College who takes part in catering class. Our statement T states that if X is true, then Y will also be true. We call a compound statement like this an implication statement. Symbolically, we can write the implication T as X implies Y. X implies Y, which is read as X implies Y. It can also be interpreted as if X, then Y, or Y is necessary for X, Y is sufficient for Y, X is sufficient for Y, or X only if Y, or X follows from Y follows from X, or Y if X. With this, we come to the end of logical reasoning. Now we are going to be treating geometry. And under geometry we have construction, as we have it here. Using a ruler and a pair of compasses only, we can do the following basic geometrical construction, just like constructing, engaging in construction that has to do with 30 degree, 60 degree, 120 degree, 90 degree, 45 degree, 75 degree, and so on. Here, under construction, we have to do with different types of construction, making use of the ruler and the compasses. Now, an aspect which is crucial under construction is locus. The locus is a set of points which satisfies a given condition or a path traced out by a point under certain given conditions. Part of the conditions, the locus of a point in the plane, which is equidistant from a fixed